Rate of energy transfer by sinusoidal waves on strings. In this lecture, we will explore how energy is transferred through mechanical waves. Our outline begins with an introduction to energy transport in wave pulses, followed by an analysis of the kinetic and potential energy found in string elements. We will then calculate the total energy contained within a single wavelength and derive the formula for the power of a sinusoidal wave. Finally, we will examine the specific factors that affect the rate of energy transfer and walk through a numerical example to see these principles in action. To understand how waves transport energy, consider a wave pulse traveling down a stretched string toward a hanging object, as shown in the diagrams. In the first image, the pulse is moving to the right. In the second image, when the pulse reaches the hanging block, it momentarily displaces the block upward. This movement indicates that work is being done on the block, increasing the gravitational potential energy of the block and Earth system. This simple demonstration proves that waves are not just movements of the medium, but a means of carrying energy from one location to another as they propagate. When we look at a sinusoidal wave on a string, we can model each infinitesimal element of the string as a particle undergoing simple harmonic motion in the vertical direction. Each small element has a specific mass and length. The kinetic energy of such an element is equal to 1/2 times its mass times the square of its transverse speed. By using the linear mass density, we can express the mass of the element as the density times the length of the element. If we substitute the expression for the transverse speed of a sinusoidal wave, we find that the kinetic energy of the element is equal to 1/2 times the linear mass density times the square of the angular frequency times the square of the amplitude, all multiplied by the square of the cosine of the quantity wave number times position minus angular frequency times time times the change in position. To find the total kinetic energy in one wavelength, we integrate the energy of the individual elements over a full wavelength at a specific moment in time. Performing this integration shows that the total kinetic energy in one wavelength is equal to 1/4 times the linear mass density times the square of the angular frequency times the square of the amplitude times the wavelength. Beyond kinetic energy, the string also has potential energy because it is stretched and displaced from its equilibrium position. A similar mathematical analysis for potential energy yields the exact same result. This means that in a traveling sinusoidal wave, the energy is shared equally between kinetic and potential forms. The total energy in one wavelength is the sum of the kinetic and potential energies. By adding our previous results, we find that the total energy is equal to 1/2 times the linear mass density times the square of the angular frequency times the square of the amplitude times the wavelength. Power is defined as the rate at which this energy passes a given point. Since this total energy passes by during one period of the oscillation, the power is equal to the total energy divided by the period. Because the wave speed is equal to the wavelength divided by the period, we can simplify the power of a wave to be 1/2 times the linear mass density times the square of the angular frequency times the square of the amplitude times the wave speed. Let us apply this to a practical problem. Imagine a taut string with a linear mass density of 5 × 10⁻² power kilograms per meter under a tension of 80 newtons. We want to find the power needed to generate waves at a frequency of 60 Hz and an amplitude of 6 centimeters. We can use a derived formula where power equals 2 times pi squared times the square of the frequency times the square of the amplitude times the square root of the product of linear mass density and tension. By substituting our values, including converting the amplitude to meters, the calculation results in a power output of 512 watts. Now consider a what-if scenario. If we want to increase the rate of energy transfer to 1000 watts while keeping the string tension and frequency the same, how must the amplitude change? We can set up a ratio where the new power divided by the old power equals the square of the new amplitude divided by the square of the old amplitude. To solve for the new amplitude, we take the old amplitude and multiply it by the square root of the ratio of the new power to the old power. Plugging in our values of 1000 watts and 512 watts, we find the required new amplitude is 8.39 centimeters. To summarize our findings, waves transport energy through a medium as they propagate, without transporting the matter itself. Each individual element of the string behaves like a simple harmonic oscillator, moving up and down as the wave passes. We have seen that the total energy within a single wavelength is distributed equally between kinetic energy and potential energy. Most importantly, the power or the rate of energy transfer of a sinusoidal wave is directly proportional to the square of the frequency, the square of the amplitude, and the speed at which the wave travels through the medium. We conclude with 2 review questions to test your understanding. First, if the amplitude of a wave is doubled, while all other parameters like frequency and wave speed remain constant, by what factor does the rate of energy transfer increase? Think about the squared relationship we discussed. Second, why is the potential energy of a string element considered equal to its kinetic energy when averaged over a full wavelength? Reflect on the integration we performed and the symmetry of simple harmonic motion. Answering these will help solidify your grasp of wave energy dynamics.